Good afternoon. Okay, in the last lecture, I talked about some algorithms learning finite state automata from given data. The data consists of several strings. And today, I'd like to talk about more about the finite state learning algorithm. Okay, this is today's content. At first, I would like to give a brief review of the last lecture, and then I will introduce some method of analyzing learning algorithm as estimation. And then I introduce the concept of identification in the limit, which is a basis of the analysis of learning algorithm. And then I give several definitions, and then I give some analysis of the simple generate and test algorithm. And also we give an analysis of pruning algorithm. Okay. Now we review the last lecture. In the last lecture, I taught an algorithm learning finite state automata, and such an algorithm takes inputs, some finite set C of positive examples and a finite set of negative examples. And each element of the positive examples and the negative example is a string over some alphabet. This is the first assumption. And the requirement to the algorithm is to output a finite set automaton M such that consistent to these two pair of examples. This consistent means that all of the positive examples is accepted by the automaton, and none of the negative examples is accepted by the automaton. Mathematically, I write in the set notation, C is included by the set of L of M. L of M is a language defined by the M. The language consists of all of the strings accepted by M. Okay? So another requirement is the intersection of the D and L of M is the empty set. Okay? This is a very simple example. This is an example of C. We assume that C consists of AB, AAB, ABBA, AB, blah, blah, blah. And the negative example consists of A, B, BBB, ABBA, and blah, blah. And our requirement is to output an automaton such as this one. This automaton accepts all of the positive examples and rejects all of the negative examples. Okay. Okay. And I give a very simple generate and test algorithm in the last lecture, and this is some modified version of the algorithm, but the essential point has not been changed. Okay. And this is based on the enumeration of all automata. You know that enumeration means in the enumeration, any automaton must be occurred in the enumeration. So, generate and test means to see the examples and take one automaton from this enumeration and check that the automaton is consistent or not. And if the automaton is not consistent, then we throw away the automaton and then choose the next one and try the check of consistency. And if it is succeeded for all of the examples, then the algorithm output the final automaton as the output, as a conjecture. Okay, so such an enumeration can be realized with in this way, because this method is based on the fact that every automaton is not a graph, directed graph like this, but it can be represented as a table. So this table is consists of finite elements, so we can enumerate all of such a type of table from smaller one to larger one. Okay. So another, I also introduced another algorithm which uses prefix tree automaton and the merging states. The prefix tree automaton is like this. For the positive example, we draw an automaton just accept all of the positive examples. The state corresponds to the prefix of each positive example. And so we have only exactly one path from the starting point to the starting state to initial state to the final state. And the final state is a leaf. And such a structure, data structure called prefix tree or trie in the algorithm world. So we said that this is a prefix tree automaton. And this automaton just accepts positive examples only. And but this automaton is overfitting to the examples, and so we have to generalize this automaton. So in order to generalize automaton, we merge two states into one. Okay? So if we merge these two states into one, then we get this automaton. And this is a generalization of this one, because in this automaton, we only starting with a single A is accepted by this automaton, but in this automaton, we have a sequence of A as long as possible, as long as we like, and then follow B and B here. So this is a generalization, and this automaton accepts more strings than this one. However, this automaton has some contradiction, because we have two choices of the string of B. So to remove the contradiction, we merge all these two states into one again, and we get this automaton. So this automaton is consistent, and so the second conjecture is this automaton. And again, we try to merge these two states into one, and then we get this one, but we have a contradiction here, and so we get this one, but we have also contradiction here. Then we eventually we get such a very simple automaton. But however, this automaton cannot be accepted as a conjecture of the learning because this automaton accepts the negative example, A, B. So, merging these states must be, cannot be, these two states cannot be merged because it makes conjecture, so contradiction. So we choose another states, this one and this one. Then we try to merge these two, and then we remove contradiction like this, okay? And then we try to these two states, and then eventually we get this automaton as a conjecture. This is the final output of the algorithm. The key point is that removing the contradiction by merging, but if for avoiding the overgeneralization, we use negative examples. Okay? Do you remember? Okay. Now, we give the first note. There might be several automata consistent with given examples, given pair of positive and negative. Okay? This is not the unique automata consistent with these two examples, these pairs of examples. So, in such automata, there is a minimal one in the sense that the number of states in it is minimal. But unfortunately, it is proof that the problem finding a minimal automaton consistent with a given pair of example is NP hard. So, solving this problem in a problem combinatorics is not so good choice of analysis. This is the analysis completed here. However, we are concerning not the optimization problem, but learning. So, I have to stress that the activity of learning algorithm should not be evaluated, not only the viewpoint of optimization. Because learning has a very wide concept, and another measurement to evaluate the algorithm should be introduced. Okay? So, for the evaluation criteria, I refer estimation from statistics. In statistics, estimation means to infer the value of some parameters from examples. Okay? And in the estimation theory, we assume that an unknown value of theta is given, but it is not unknown. The parameter theta affects the structure of d of theta. In statistics, it is a distribution on data, but in our theory, it's just a set. And only finite number of data are coming from the set or distribution. And we expect that more data from d of theta, then better conjecture could be obtained. This is a key idea or fundamental foundations of estimation. And in learning finite state automata, we let the parameter n for finite state automata and the formal language theory. L of M be the set of data corresponding to D of theta. More precisely, we assume that an unknown automaton is provided, unknown automaton M is provided, but it is unknown for us. Only God knows about that. All that we can observe or we are provided is positive examples and negative examples. And the positive examples means that it is an element of L of M. Again, this M is unknown. And the negative example is from the coset of L of N. Then, in such a case, we assume that X is marked with plus and X with minus, with a polarity. Okay. Then, next we have to define is that 2 points. If we give more and more examples on M to a learning algorithm, then does it eventually conjecture the unknown automaton M correctly? This is not the problem of optimization, but somewhat on the evaluation of learning activity. Training, then the learning algorithm eventually find or reach the correct answer or not. Then we have to give a mathematical definitions of what is giving more and more examples, and what is a conjecturing M eventually or finally. More intuitive here. This red part is assumed to negative examples, and this green part should be positive examples. And providing more and more examples means that these green part and these red part are coming to the boundary of L of N. In such a situation, the learning algorithm conjectures M correctly or not. And to give the answer first, the two algorithms, generate and test method, and the pruning algorithm, both of the two algorithms satisfy this property. So, even though we failed to provide a good evaluation as an optimization, but the two algorithms have a good property as learning algorithm. Okay? And to give mathematical definition, we first give some assumption. And at first, without loss of generality, we may assume that learning algorithm takes examples in C and D one by one. Okay. This is a very natural algorithm when we write down a program of learning algorithm. And the second, in the situation that both C and D grow, we assume that an infinite sequence of sigma of strings marked with some polarity and some truncation sigma correspond to the union of C and D. this means some example. We give, we don't consider about the two sets C and D, but we consider infinite sequence of examples. Each of the examples is provided attached some polarity plus and minus. Minus means this is a negative example, and plus means positive example. And instead of considering the pair of C and D, we consider the infinite sequence of sigma and some truncation. Truncation means some prefix of the infinite sequence, and get together the positive examples as C and the negative examples as D. So these two are equivalent. This I mean that provided C and D is equivalent to consider the infinite sequence and its truncation. Then this sequence is infinite, so we can consider some convergence or some other concept from mathematics. Okay, then we give definitions. A presentation of formal language L of M is an infinite sequence of pairs, where each of the pair consists of some strings and its polarity. So x plus, the polarity plus means it is a positive example, and x minus means that it is a negative example. And the truncation is represented like this. It is the first, the prefix of the sequence, its length is n. Okay. And the presentation sigma is complete if any element x in the target language appears in sigma as a positive example, and any x appears in sigma as a negative example. Something strange. Sorry. This bar should be put here. Okay. Intuitively, this is a sequence, so we can define the convergence. And this sequence converges to the set of all positive examples and all negative examples. It is quite difficult to define the convergence of two sets, but the convergence of sequence is very easy. It is high school mathematics. Okay. Now, we give the definition of the property of as estimation. A learning algorithm A, Ex identifies L of M in the limit from complete representations if for any complete representation sigma of L of M and the output sequence M1, M2, M3 of A, there exists n such that for all n more than n, the conjecture M of n is some m prime where the language of L prime is equal to the language of L of n. This is a very complicated, but I give an example. Okay, we first consider enumeration of finite state automata. So we give, please consider about the generator and test algorithm. Generator and test algorithm is take one example and take one automaton and check the consistency. It's okay, then output as a conjecture. And next, we take another example here and check the consistency to the two examples. And if it is succeeded, we keep the automaton. But if the automaton is not consistent to the two examples, then we throw away the automaton and take the new automaton from this list enumeration. This is an enumeration method, generator and test method. Okay, more precisely, as I told last lecture, this is the first part of the enumeration of finite state automaton. Here, this is a very simple automaton, only consists of only one state. And this automaton is also consisting of one state. And then we turn into the automata consisting of two states. And then consider the input sigma presentation. And the first example is AB with positive sign. So this must be positive example. And the first conjecture, the starting point is here. And as you can see, this automaton cannot accept any string. There's no finite state here. So we throw away this automaton as a conjecture, and next we check this one. This is the second simplest automaton in the list. And this automaton accepts all strings. So, of course, this automaton is consistent with this example. So, first we keep this automaton as the first conjecture. Next, we show the second example. The second example is also positive. So there's no contradiction between the two examples and this automaton. So we keep the consistent automaton here. And the third example is BB minus. Minus means negative example. But this automaton accepts this BBB because this automaton accepts all strings. So we have to throw away this one and choose the next one here. And check that this automaton is consistent with these three examples. Do you understand? However, this is not consistent to this one because BBB is accepted. So this automaton cannot be the candidate. So we go to the next one here. Then this automaton accepts all these two strings but rejects this one. So this is the second conjecture here. Then we get this truncation. And the next example is, for example, AAAB with polarity plus. and check the consistency of this one and this one. It's okay, so we keep the conjecture here. And in such a way, we perpetually continue the getting an example and revising the conjecture if needed. If needed means that the conjecture is consistent or not for all the examples. And the identity in the limit, EX identified, requires that in some point here, the learning algorithm output a correct one. Correct means that the language of the output is equivalent to the unknown automaton. And the learning algorithm never changes the conjecture forever afterwards. This is definition EX identified. If you are very good at mathematics, this is a kind of convergence. So sometimes I say that the conjecture of learning algorithm converges to the correct one. And the definition provides what is a convergence. Okay? So, and then at this moment, please note that for a finite set automata M, there might be another, another automaton such that L of M is equal to L of M prime. For example, for this automaton also accepts the same languages. This automaton accepts strings which contains the even number of b's. And this is also such an automaton because we have 4 states, and here shows the number of b is even. So these two are equivalent. But in the theory automata says that there exists a minimum one. Minimum means the number of states is minimum, which is in the equivalent class of automata. And the generate and test algorithm outputs this one if the enumeration is made by the number of states, just I showed before. Okay? So this is a very well-known result on finite state automata. For every language, LM, accepted by a finite state automaton M, there is a unique minimal automaton M prime such that L of M is equal to M prime. So we cannot write here M equal, here we cannot write M, but M prime, which is a state minimal automaton. But it might be different from the unknown automaton. But it should be equivalent as accepted languages. Okay? So this is a very tiny point, but the definition is so complicated. But the intuitive meaning is that the algorithm must be converged to the correct unknown automaton, just providing the complete presentation of data. So, in such a sense, this generate and test mechanism framework is very good property as learning algorithm. Okay. So, hence we propose such a property, we sometimes use a mathematical presentation. So, for any finite state automaton M of sigma, the modified generate and test algorithm EX identifies L of M in the limit from complete presentations. Why? This is a proof, very rough proof, rough sketch of proof. Let sigma be any complete presentation on L of M, and L of Ln be the output, L sub n be the output of the algorithm for the input for the truncation of sigma. If the two languages are different, the two language means that the language generated by the unknown automaton. And this MON is a current conjecture provided by the learning algorithm. If these two are different from each other, this means that from the definition of mathematics, there is a data X in L of M which does not belong to the L of Mn, or there is an X which does not belong to L of M and X belongs to L of N. This is a definition from set theory from mathematics. So I don't use anymore. So current conjecture. This is unknown. This is the unknown automaton. And these two sets are different, means there is such an element here or such an element here. I mean that in such a situation might happen. So I said that this holds over this holds. Okay? And since sigma is complete means that complete means that whole of these data appears in sigma as positive examples, and 4 of these parts appears in the negative example in the sequence presentation sigma. So this point must appear, this data must appear in the presentation, and this data must appear in the presentation. In such a situation, this conjecture must be rejected and revised. So, such a situation happens, we assume that L of M is not L of Mn. So, this means that L of N must be replaced with another automaton at the latest when X appears on sigma. Once the algorithm outputs Mn such that L of N equals L of M sub n, then it never changes the conjecture because of activity of algorithm. This is the definition of the algorithm. So, the algorithm, the output of algorithm converge to the correct unknown automata. Okay, do you understand? Some tricky? But understanding such a discussion is the milestone of the first milestone to the analysis of learning algorithm. Okay. Okay. Then second is the linear algorithm is also the property of identification in the limit, EX identification in the limit, or not? And the answer is yes. A slight modification of pruning algorithm fit the framework, so it is not the essential, but I would like to propose that for any finite set automaton M of sigma, the pruning algorithm EX identifies L of M in the limit from complete presentations. This is a proposal. And why? To show the theorem, we first introduce a characteristic set of positive examples. A set of positive examples is characteristic for the pruning algorithm if for every finite state QF there is a string X such that the X should be reached to the finite state for a final state, and for every truncation delta for transition delta of A, which can be used for accepting some string X, there is a string L such that the transition is used in accepting Y. And this is a very complicated definition, but the intuitive meaning is very easy. For example, this is a target automaton, a known automaton. And the characteristic set is this one, consists of only 2 strings. Characteristic, at first, we have only one final state here. And the second one is that we have several transitions from here to the final state. And in this characteristic set, every transition from the initial state to the final state must be appeared as bigram. For example, this is A, A, B, B, A, A, B, B. So A, A, B, B means that this string is accepted by this transition and this transition and this transition, this transition. So this string has all information from here to here on the transition. And this ABB is also another transition here. A, B, B, B. So this here, something wrong. A, B, B. Something wrong, sorry. Correct one is BB, A, B, A, B. Sorry, this one. So, by using this string here, A, B, A, B. So, with these 2 strings, we have all information on transition from the initial state to the final state. And the transition appears by adding this here as a empty string here. We have bigram. In the sense, I said this 2 positive examples, this set of examples is characteristic, which keeps all information how the automaton accepts strings. Okay. Then we write down prefix tree of this positive example like this. Okay. Then the goal is very simple. If we merge several states very properly, we have to show that if we merge several states into one very appropriate manner, then we get this automata from this one. But maybe it is very clear, because I told you just before that this sample has all information on transition needed to accept a string as bigram. So any transition appears as a transition here in somewhere. So the solution is here, right one? Merge blue state into one and merge red state into one. Then we get this one. Of course, we have a dead state here, but we omit here this one. This maybe this property is understood all of you. The key point is all transition appears here. However, the important point on the pruning algorithm is a negative example or overgeneralization. I said that I merge states very proprietary, then I get this automaton. But if we have no negative examples, then the pruning algorithm outputs very simple automaton, which consists of only one state. So we need some negative examples to avoiding the overgeneralization and to induce the algorithm to this correct automata. To find such a negative example, set of negative examples is not so difficult. And so I put it as a homework to you. But in the context of EX identification, much easier solution can be found. So again, we are considering the EX identification. So EX identifies considers that we have a perpetual infinite sequence of inputs. So just all that we have to do is that when we have some overgeneralized automaton as output of pruning algorithm, just wait sufficient negative examples, because we are assuming that again all of the positive examples and all of the negative examples appears in the sequence of sigma. So overgeneralization means that the conjecture of the output is much larger than the unknown automaton. But in such a case, as I told you, that such an example comes, negative example comes eventually. And at that moment, such an overgeneralized hypothesis is thrown away, even though we use a pruning algorithm. And we get another automaton with the merging strategy. And eventually, we have enough number of negative examples. We reached to the correct automaton. So, pruning algorithm works as learning algorithm. It means that the output converges when we get more and more data to the learning algorithm. Mathematically, we give us definitions, and again, we refer the prefix tree automaton here. These are very simple definitions. Prefix is all of the prefix of positive example is used as a states, and we give a partition of the states is a set of subsets of states. Each of state subset is non-empty, and every pair of the subsets is disjoint, and all of the unions of all of the subsets are covered with a Q. Sorry, this is a Q. Then every BI is called a block of pi, and a block represents the merged states of Q1, and we give some consistency of the blocks, and then we can define the quotient. Quotient means that merged automaton as a mathematics. So then the merged automaton is represented as m/pi. Then at first we give this lemma. For finite state automaton M, let M prime be the minimal automaton satisfying L of M is L of M prime. And let C of M be the characteristic set of positive examples of L of M prime. Then there exists a consistent partition pi of the prefix tree automaton such that m/pi is equivalent to M of prime. Again, for a finite state automaton, we have several automaton which is equivalent to the original automaton. So when we discuss such a type of property of automaton, we usually use a minimal automaton. Minimal means the number of states is minimal. Okay? And this property is, this lemma is just I explained before. The key idea for the proof is that C of M prime contains every transitions of M as a bigram of strings in it, and every bigram is replaced as an independent transition in M of C and M. Okay? Then, if for any finite state automaton M of sigma, the prune algorithm EX identifies L of M in the limit from complete representation. The sketch is right down here, but the very rough explanation like this is maybe enough. All that I would like to know to explain is that if the output is overgeneral, then such a negative example, which shows that the hypothesis conjecture is overgeneral, comes eventually. And in such a moment, we can revise the algorithm to run the pruning algorithm again. Okay. So, these two theorems I showed here are support of the two algorithms as running algorithms in the sense of EX identification. Of course, we have other evaluation method of algorithm as running algorithm, and the EX identification is very classic one. But it just corresponds to the statistical estimation. So as a first milestone, I introduced the criteria evaluation method for evaluating algorithm. Okay. Questions?